A warm welcome to the third lecture on the subject of digital signal processing and its applications. Let us take a couple of minutes to review what we did in the previous lecture. In the previous lecture, we had initiated our discussion on sampling. We had tried to answer the question, when can we retain information even after sampling? To expand a little bit, when can we consider values of a signal only at sampling instance and yet not create any confusion or not lose information? We had not completed our answer to that question. We had only got thus far, and we shall now summarize that. So, let us put down the theme of our lecture today: reconstruction from sampling, or from samples to be more appropriate, aliasing, and discrete systems. This is the theme of our lecture today. Well, what we had seen the last time is that if you have an original sinusoid of frequency 0.1 kilohertz, and if you have a sampling rate of 1 kilohertz, then you land up with a confusion of sine waves. And the confusion is as follows. On the kilohertz scale, the samples could have come either from a 0.1 kilohertz frequency or from a 1.1 or a 0.9 kilohertz frequency, and of course, if the amplitude of this is A naught and the phase phi naught, the amplitude of this is A naught phase phi naught, the amplitude of this A naught phase minus phi naught, the amplitude of this at 2.1 is A naught phase phi naught, and we can keep doing this. Amplitude A naught phase minus phi naught, we can continue. So, at every multiple of 2 kilohertz, we have these confusing sine waves, if you want to call them that, which contribute to the same samples. Now, I want to say a little more about this observation. You see, what we had shown in the previous lecture was that all these sine waves generated the same samples at those instants. However, we need to show something more. We need to show that if I indeed add up these sine waves, as I have shown here, with amplitudes A naught and phase either phi naught or minus phi naught, depending on whether it is after the sampling frequency or before, if I add up all these sine waves, I generate what I really call a train of samples. And what do you mean by a train of samples? In fact, this is a challenge which I put before you. It is a practice that I follow in courses that I teach to challenge your imagination right from the beginning, to put before you exercises which will make you think and work certain things out on your own, so that you get a much better grasp of the ideas that are being taught. And we are beginning with the first challenge. these sine waves and add them one by one. What I mean by that is, take the sum a naught cos omega naught nt plus phi naught. Or in fact, let us not sample, at nt of course you will get infinity, there is nothing much to be seen. But let us instead add up the continuous. So, we should say not these sinusoids at the samples, but sinusoids, the continuous sinusoids. So, 2 pi by t as we would have it minus omega naught times t minus phi naught plus a naught cos 2 pi by t plus omega naught times t plus phi naught plus, now what will come next? Let me do it for a few terms for you. So, what I mean is, you see, you have taken the original sine wave as a continuous sine wave here. You have taken the next one is the sampling frequency in radians per second, 2 pi by t minus omega naught, and then the phase would be minus phi naught. Sampling frequency in radians plus omega naught plus phi naught. Now, the next term would be 2 times this sampling frequency in radians minus phi naught, and the next term after that would be 2 pi by t times 2 plus phi naught. So, let me write down 2 more terms to make the concept clear here. Let me write it down completely. You can keep on writing more and more terms. Anyway, we have got the basic idea. Now, the challenge before you is to prove that as you add more and more terms, you have a constructive interference at the point of sampling and a destructive interference at all points other than that of sampling. In other words, what I want you to prove in the challenge and let me write that down. Prove that this sum is constructive at the points of sampling. that means t equal to nt, and destructive at others. So, what is going to happen? As you add more and more terms, essentially this sum is going to become localized near the points of sampling. It is going to rise higher and higher. In fact, it is very easy to see that at the point of sampling the sum is divergent. It would go towards infinity. We knew right in the beginning from the previous lecture that the samples are the same when they come from all of these sine waves. So, at the points of sampling, of course, constructive interference is obvious, because all the samples are the same, all the values, all the sine waves take the same values. The key thing is to prove that at other points the sum is destructive. That means, as you add more and more and more and more terms, they all compete and cancel one another out. So, I leave this as a challenge to you, and I give you a hint. You will have to use trigonometric identities. You are summing up sine waves of the same amplitude of different frequencies. Use trigonometric identities and show and try and see what they are converging to, what that sum converges to. If you like, you could decompose a sine wave into a sum of two oppositely rotating complex numbers, as you often do. So, that is also acceptable. We will be dwelling on that idea in more detail later. They are called phasors. Anyway, for the moment I am putting this before you as a challenge. Why I am saying this is because it tells you what happens when you sample. When you sample, what you are doing is essentially to create small pulses at the instance of sampling of value or strength equal to the sample value of the waveform at that point. At all other points, you essentially have a 0 signal. So, sampling means to replace a continuous signal by a train of pulses, idealized sampling. Means to replace a continuous signal by a train of pulses, sharp pulses, if you would like to call it that. Let us sketch what we are saying. What we are saying is, if you have this continuous signal, and if you sample it here and here and then here and here and here, what you are doing is just ultimately considering this signal. So, let me call this x s of t, and let me call the original signal x t. Now, what is the purpose of reconstruction? The purpose of reconstruction is to get back x t from x s t, simple. And where is the problem? Now, we know the problem. The problem is not that you do not have an x t which you can get back, you have just too many of them. If x t, even if x t were one sine wave, this process of sampling has created an infinite number of sine waves which could have generated those samples. So, the problem is not that you have no xt, the problem is you have just too many xt's which could have all resulted in the same set of samples. Now, the difficulty is to identify which is the correct xt, and that is where we need to see when we will be in a position to do so. You see, a simple approach to identifying the correct xt is to go back to what we did on the frequency axis. On the frequency axis, what sampling does, sampling creates copies. At a collection of frequencies. In fact, let me try and illustrate this to you with an example, or at least with some intuitive explanation. So, we have done the exercise for one sine wave, but let us do it when you have a few sine waves. So, suppose we have a few sine waves. We have a 0.1 kilohertz sine wave, we have a 0.13 kilohertz sine wave and a 0.15 kilohertz sine wave. So, what is the copy that is created? Around 1 kilohertz, when you sample at 1 kilohertz, again, you have, so what I am saying is you have these three, and in fact, let us give their amplitudes some values. So, we could say this has amplitude A1, phase phi 1, this sine wave has amplitude A2, phase phi 2, and this one has amplitude A3, phase phi 3. Then, if the sampling rate is 1 kilohertz, or sampling frequency is 1 kilohertz, if you prefer to call it that, then you get a copy at around 1 kilohertz, you get 1.1, you get 1.3 and you get 1.5, and of course, the amplitudes are A1, phi 1, A2, phi phases, amplitude and phase I mean, A2, phi 2, A3, phi 3 here, and you also get copies behind. So, you get 0.9, 0.7, oh well, I am sorry, this should be 1.1, this should be 1.13. So, in fact 1.15. So, this would be 0.9 and this would be 1 minus 0.13, that is 0.87, and this would be 1 minus 0.15 and that is 0.85. The amplitudes here would be A1, A2 and A3 respectively, but the phases would be minus phi 1, minus phi 2, minus phi 3. And you can keep doing this exercise. You can do it around 2 kilohertz, you can do it around 3 kilohertz and so on. But the central idea is that you have this original what we call spectrum. Now, we will bring in the word spectrum. Spectrum is the decomposition of the original signal in terms of the sine waves that comprise it. You have this original spectrum. So, let me repeat, what is a spectrum? Essentially, a spectrum is a Fourier transform. What is the physical meaning of the spectrum? The spectrum is essentially the collection of sine waves specifying the frequencies, amplitudes and phases. Now, here we have a discrete set of frequencies. We have 0.1, 0.13, 0.15. We could have a continuum of frequencies. So, remember, if the signal is aperiodic, then we need to have a continuum of frequencies. The frequency axis could be continuously occupied in a small segment. Then you have a band of frequencies occupied. In fact, you talk about the band of frequencies on which the signal lies. So, here for example, we have taken a case where there are only 3 frequencies, 3 sine waves, 0.1, 0.13, 0.15. So, the band of frequencies is between 0 and 0.15. But of course, you could have a continuous occupancy of the frequencies all the way from 0 to 0.15. So, we will say in either case that the band of frequencies occupied is between 0 and 0.15. The difference is here we have a discrete set of frequencies occupied, you could have the continuous axis occupied all the way from 0 to 0.15. Whatever it is. What is the effect of sampling? The effect of sampling is that the original spectrum is copied as it is after 1 kilohertz, after 2 kilohertz, after 3 kilohertz and so on, and it is copied in mirror image fashion. So, you can visualize this has been mirror imaged, and in mirror imaging you have reversed the phase as well. So, you have a copy of the original spectrum here, and a mirror image of the spectrum here. And this is repeated at every multiple of the sampling frequency. So, around 2 kilohertz, you have a copy of the spectrum after 2 kilohertz, and you have a mirror image of the spectrum behind 2 kilohertz. In mirror imaging, the phase is also reversed. So, it is very easy. How do you reconstruct xt from xst? If you look at the spectral domain, it is very easy. In the spectral domain, what we need to do is to retain this and throw away this. Throw away not only this, all such copies. Let us write that down. It is a very simple idea. Reconstruct xt from xst means retain the original spectrum and throw away the copies, all copies and mirror images in fact. Now, the answer is very simple. When can you do this? You can do it if the copies and the mirror images do not mix with the original spectrum. Let us write that down too. We can do this if neither the copies nor the mirror images pollute or overlap the original spectrum. And again, now we have a simple answer. Which is the trouble making copy or mirror image? In fact, if you think about it, it is only the first one which is the troublemaker. And that too not the first mirror, not the first copy. It is the first mirror image which is a troublemaker. That is the one which comes first as you move away from the original spectrum. So, let us write that down. The troublemaker is essentially the first mirror image. So, you see, again let us write this down on the frequency axis, and this time let us use more general symbols. Let us not confine ourselves to this 1 kilohertz, 0.1, 0.11 and so on, right. Let us use 0 to Fm, this is the maximum frequency or the band occupancy. So, we will say that this whatever sine waves there are in the signal are all between 0 and Fm, and the sampling frequency is Fs. So, the first mirror image occupies the range between Fs and Fs plus Fm. I am sorry, the first copy. The first copy occupies the range between Fs and Fs plus Fm, and the first mirror image occupies this range, Fs and Fs minus Fm. So, now we are very clear, as long as this point is after this point, we are okay. So, all that we need Fs minus Fm should be greater than Fm, or Fs should be greater than twice Fm. Now, this is a very simple principle. This is called the Nyquist principle of sampling. In fact, I dare say many of you probably know this principle. You know, this is called the Shannon, Nyquist, Whittaker. There are so many names associated with this principle. In fact, many people have arrived at this conclusion by using different approaches. We have also used a simple approach to come to this conclusion, perhaps a little intuitive, maybe not that rigorous, though we can complete the same discussion with rigor.